In this section, we will discuss about the energy of the simple harmonic oscillation. In general, the kinetic energy of an object K is equal to the half of the mv square. We all are familiar with this formula, but for the simple harmonic motion, we know the value of v as a function of t. So if we substitute v to this equation, we will have that the kinetic energy is equal to the half of the m omega square a square sine square omega t plus 3. Okay, so this is the formula of the kinetic energy. Now, we have discussed before that we can define the potential energy, the elastic potential energy of the spring. The elastic potential energy of the spring, and is equal to U equal to the half of kx square, and if we substitute x here, we will have that U is equal to the half of k square a square cos square of omega t plus 3. Okay, so we have the expression of k and u, but we also know that from these two equations, we know that omega is equal to the square root of k over m, so omega square is equal to k over m. So if we substitute this relation to the expression of the kinetic energy, and then we sum up the kinetic energy and the potential energy to get the total energy of the system, we must have that E is equal to K plus U and equal to 1/2 of Ka square sine square omega t plus 3 plus cos square of omega t plus 3. Okay, but from the trigonometric identity, we know that the last term, this term, the sum of sine square and the cos cosine square is equal to 1. So what we have is that the total energy of the simple harmonic motion is equal to half of Ka square. This is the total energy of the system. You can see that the total energy of the system depends on the amplitude and the spring constant. The amplitude of the system and the spring constant. And you can also see that this term half of Ka square is a constant. So it means that the total energy of the system does not change in time. Or we can also say that the total energy of the system is conserved. And this is agree well with the property of the Hooke's law, the force that obey the Hooke's law, because we have shown in previously that the force from the spring that obey the Hooke's law is a conservative force. So it means that the total energy of the system will not change in time. And we can see this here, that E is equal to the half of Ka squared. K is a constant, A is a constant. So it means that the total energy of the system is a constant. And the total energy of the system is conserved. Okay. If we draw the graph of K and U as a function of time, we will have something like this. This orange line is the kinetic energy, and the the orange line is the potential energy. Okay, it is defined here, and the blue line is the kinetic energy. And since the potential energy is in the form of cosine function and the kinetic energy is in the form of sine function, they have the 90-degree out of phase. It means that when the kinetic energy is maximum, the potential energy is minimum. And this is reasonable because the maximum value of the kinetic energy happens when the velocity is maximum, and it also means that x is 0. The object is at the equilibrium position. So at x is 0, the potential energy, which equal to the half of the kx squared, is 0 here. So at the equilibrium position, the kinetic energy is maximum, while the potential energy is minimum. The situation is totally different when the potential energy is maximum. You can see that at this point it means that x is equal to a. It is at the x is equal to the amplitude of the oscillation, which means that v is equal to 0. Okay, because x go to the maximum displacement, so it means that it cannot go beyond that point, and the velocity must be 0. So when x is maximum, the potential energy is maximum, and because v is 0, the kinetic energy is minimum. You can see that the potential energy and the kinetic energy change in time, vary with time. But when you sum up these two terms, the orange and the blue line, it will become a constant which equal to the half of Ka squared. And this confirms that the total energy of the system is conserved. Okay. And from the conservation of energy, we can also write down the equation energy as E is equal to the half of mv square plus half of kx square, which equal to the half of ka square. We can solve this equation to get v as a function of x, and if you do that, you will have that v is equal to the plus or minus of square root k over m of a square minus x square. The plus minus sign here means that at the same value of x, or at the same position of the object, the velocity can have both positive and negative value. And since we use the sign to represent the direction, so it means that at the same value of x, we can have both the positive direction or negative direction, and this is obvious. You can see that at the same position, sometimes the object move away from the equilibrium, but sometimes it can move toward the equilibrium. So we can have both positive and negative here. And from this equation of v, you can see that we can write down the kinetic energy as a function of x, right? If you substitute this value of v to the expression of the kinetic energy, you substitute v to the expression of kinetic energy here. You can, and you plot k as a function of x, you can see that we will have this blue curve. This is reasonable. At the maximum displacement, the x is equal to a and v is equal to 0, and the kinetic energy at this point and this point is 0. At the equilibrium point, where x is equal to 0, v has a maximum value, and this is the peak of the curve of u, the kinetic energy. Yellow line, orange line represent the potential energy and is opposite to the kinetic energy. When the kinetic energy is 0, the potential energy is maximum. When the kinetic energy is maximum, the potential energy is 0. And if you sum up the value at any position x of the blue curve and the orange curve, you will get a constant that equal to half of ka square. Again, it confirms the conservation of the energy of the force that obey the Hooke's law.